Alright, well, so far we've come a long way to be able to mathematically represent what a computational model is. In this case, the computational model for a finite state machine, which is the bread and butter of a lot of electronic applications, digital electronic applications. And we are going to actually start building a toolbox for a toolbox that would help us for designing automata to recognize particular languages, and in our case it will be called regular languages. What we want to do is for this toolbox to include is ways of proving that certain languages are regular, that certain machines that we can formally define could recognize these languages, which then will help us develop our computational needs and then be able to mathematically work with them, and then also to be able to infer about whether a language is actually beyond the capability of a finite automata to work with. And in this case, we would call these languages non-regular languages. Once we realize what these languages are and what the capability and the limitations of our automata is in recognizing languages, then we'll be able to define additional computational models that would help us work with these new languages, or rather these other languages that are not regular, that are beyond the capability of our finite automata. So before we are able to do so, we actually need some operations to be able to work with languages. In arithmetic, basically, your basic mathematical objects are numbers, and the tools that you work with these numbers are your arithmetic operators. And those are basically plus and multiply. If you have two objects that are numbers, you can combine these numbers to get a new number with adding them or multiplying them with each other. In the theory of computation, the languages are the objects that we work with. So in our case, we don't care about numbers. All we care about is a set of symbols, which is our alphabet, and then the strings that we can make out of these symbols, we call those, of course, strings or sequences, and then grouping of certain number of or even an infinite number of strings that possess certain kind of property. We would be interested in those massive sets, and those sets we call them languages. So since we are manipulating languages, and as such we're manipulating strings or sequences of symbols, we need to include tools that are efficiently designed to specifically work and manipulate languages, or language parts, in our case strings. These tools, we call them regular operations. There are a number of these regular operations that we can work with, but effectively we are interested in actually 3 regular operations, and I personally I'm interested in 5 operations, but 2 of these operations are fairly straightforward, that we can deduce them from these 3. So one of the regular operations that we're interested in, is called the union operation. Of course, if you remember, when in the first unit we talked about basic terminologies in math, we said that a definition of a set is a grouping of numbers, an unordered grouping of numbers. Grouping of elements. So a set of natural numbers is 1, 2, 3, 4, 5. Set of integers is negative infinity all the way to 0, and then 1, 2, 3 all the way to positive infinity. And the set of, I don't know, weather conditions would be sunny, cloudy, hurricaney, or whatnot, right? So since we work with languages, we can consider, and we actually by definition consider each language to be a set. So as a result of that, one of the operations that we have over 2 sets is called a union. So when we work with languages, this union is a regular operation that we would be able to use to combine two languages with each other. And of course, the definition of union is just nothing new. It's just the same definition as the definition of union for sets. The union of A and B, and we show it with this little cup symbol, is equal to X, such that X is a member of A or X is a member of B. Notice that this OR is actually a logical OR, and if you have the set X that's a member of both A and B, it will be a member of their union as well. So this is an easy operation to define. The next operation that we define is called the concatenation operation. We didn't specifically talk about this operation in terms of sets, because that wasn't useful back there when we were just talking about generic sets. But when it comes to working with languages, which are a special kind of set, we can use this operation called concatenation. What that means is that if you have a set A, two sets A and B, the concatenation of set A and B is the set of all elements, all strings, that can be combined in this form. They can be broken down into two parts, X and Y, such that X is a member of the first set A. So X is a member of the first set, and Y is a member of the second set. So basically, if you have, I'll show you a couple of examples of these operations for some sample sets and languages, and we'll see. So concatenation is you have a string from one set, another string from another set. If you just put them together so that the second one will start immediately after the first one finished, then that is the concatenation operation. We say that you concatenated two strings with each other. In this case, again, X and Y are strings. So in all these cases, X and Y are strings. And A and B are languages. Okay. Now, the next operation is the star operation. The star operation is applied on a set. And what it does is that it basically makes a superset of the language, like a super language. And so the star operation starts with your original set, and then it includes all of the strings in your original set and any number of concatenations of these strings with each other and with themselves as well. So it's like a complicated spaghetti bowl of strings within your language. That is your star operation. So formally we define it as such. A star is a set of x sub 1, x sub 2, x sub 3 to x sub k concatenated with each other such that for k greater than or equal to 0, each x sub I is a member of A. What that means is that if you pick k as 0, you have no strings, it's empty. If you pick k as 1, it's every single string in your set. If you pick k as 2, it's every 2 strings concatenated in your language. If you have k equal 3, then every 3 string in your original language concatenated. And it goes to infinity, which means that you basically concatenate every string with every other string and in any kind of combinations of them to create this A star. So star is like a ridiculously large set. And in fact, it would be an infinite set, even if your set has just only 2 elements in it, and we'll see. So let's see a couple of examples and see how they work. So let's say that set A is made of 2 strings, good and bad, and set B is made of 2 other strings, boy and girl. The union operation of A and B, so again, these are languages, right? So this is a language. And this is a language. And these guys are basically just strings. And don't really pay any attention to the meanings of these things. These could have equally been just 0 1s for that matter. At this point, we really don't care about, because we are mathematically defining things. So So the concatenations of these two languages is the language that's made of 4 elements, 4 strings: good, bad, boy, girl. Now remember, since A union B, did I say concatenation? I meant union. So A union B is equal to just these 4 unordered strings. You could say it's good, and then boy, and then girl, and then bad. Or any permutation of these things work, because with sets, if you remember, order does not matter. So all of these are equally the same set. In concatenation, though, notice that each member of B comes after each member of A, right? So when you concatenate the sets A and B, you get good boy, good girl, bad boy, bad girl, right? If you concatenate B with A, so the concatenation of B and A is going to be this new language, and each member of B will come first. So you've got boy, good, boy, bad, bad, and then girl, good, and girl, bad. And this is a concatenation. Now, could I swap these elements? Sure. So it could be boy, bad, and then girl, good, and then boy, good, and then girl, bad. As long as the first part of my string is from set A, and the second part of the string is from set B, I'm good. Actually, the other way around. Set B and set A. So as long as the first part is from set B and the second part is from set A, the concatenation is good. And finally, with the star operation, remember we said that the star operation, or A star, is the language that has all of the strings in it that are of form x sub I, x sub j, and so forth, or rather x sub 1, x sub 2, x sub k, for every k, positive and 0 k, such that x sub I is a member of A. Okay, so what that means is that when k is 0, when k is equal to 0, if I can write, then the member is going to be x sub 1 to x sub 0, which can't be, which means that that member is going to be epsilon, or the empty string. When k is equal to 1, then you will have all single strings. So in my case, I've got good. So all of my single strings are good and bad, right? When k is 2, then that means that all pairs of strings, right? So in my case, it could be good and another good, good and bad, bad and good, bad and bad. Okay, every 2 pairs of the strings that you have. So since I have 2 in my original set, I've got 4 in this. If k is 2, I've got 4 of the strings that you could, 4 combinations of these pairs of strings. When k is 3, then that means that you got all 3 tuples. So it could be good, 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 and then good, good, bad, and then good, bad, good, and on and on and on. So basically I've got 8 of these. And for k equal 4, I've got 16, and so on and so forth. But notice there's these dots at the end. This indicates that this set goes on and on to infinity, because we didn't specify any bound, any upper bound on k here. See, in here we said that A star contains all the strings that are all combinations of strings for any numbers of k greater than or equal to 0, which means that you can have an infinite number of strings from your original strings just mixed with each other, concatenated with each other, and they'd be a member of A star. So these are the three languages that the three operations, regular operations that we're interested. We call these operations regular because regular languages are closed under these operations, and we'll talk about this shortly. But there are two other operations that I didn't really specifically mention, which are interesting and have merit to talk about them a little bit. One of these operations is the intersection operation. If you have two sets A and B, two languages A and B, the intersection of these languages is basically the set of all strings X such that X belongs to both of these strings. To both of these languages. In this case, because both the language A was made of string good and bad, and language B was made of boy and girl, just these strings, then the intersection of A and B is actually the empty set, because there's no string that belongs to both of these languages. But in certain cases, you may have languages that may have strings in them. For example, the set of all strings that has a substring 0101 in it, intersection with the set of strings that have two zeros in them, right? So as you can see, there is intersection between these two languages. So intersection is an important operation. Interestingly enough, when we work with the closure, once we prove the closure for the union, the closure of intersection just comes naturally out of it, and we talk about it as a corollary, basically. And so when we talk about intersection, rather union, it's dual, rather it's twin brother intersection follows. Another operation that's also very important for us to kind of look at least at this level, is the complement. So the complement is an operation that is performed on a language, and it will be basically all the strings such that X does not belong to your original language. For example, if these languages were coming from the English letters A through Z, then the complement of A would be every other word in the English language, as well as all the non-word combinations of letters that are not good or bad. Okay, so complement is another language that might be of interest for us. Why I'm talking about these is that if we prove that the regular languages are closed under these operations, as we will see in a couple of minutes, and you are given a language and asked to design a finite automata for them, or even a non-deterministic finite automata, which we will see later in this class, probably in the next unit. There are certain languages that you can break them down into smaller languages, and then you can use these operations to create finite automata for those smaller languages, and then build up to create the automata that you want for the bigger, more complex language. In fact, in your next assignment, you will be given a couple of these questions to do. So this is so far a good start for this part of going through the unit. We now have the definition for our regular operations: union of two languages, concatenation of two languages, and the star of a language. And next we're going to go over and start working with a very important theorem. Actually, sets of theorems. and those involve closures. Okay, here we are. Our first mathematical proof of the class, and hopefully not the last one. A very important theorem about regular languages. The theorem states that the class of regular languages is closed under the union operation. Remember, union was one of our regular operations that we discussed earlier. So, looking at this in the English form, it looks pretty beautiful, but it's kind of useless because none of these words really mean anything to me mathematically. However, here's what mathematically matters to me are these facts, these important things. This is a conditional statement, which means that if a certain condition meets, so is the other condition. So it's an implication. So if the premise is true, according to this theorem, then the rest of this statement is true. So if I have two languages, A sub 1 and A sub 2, and if these two languages are regular, then their union is also regular. Now, let me just give you an analogous version of this statement with numbers, which you are quite familiar with, or should be at this point, and that is the set of natural numbers and the operation plus. Now, if I'm talking about the set of natural numbers, the set of natural numbers is a set, basically, that has a bunch of numbers in it, whole numbers, right? 1, 2, 3, 4, all the way to infinity. And if I define an operation plus that takes two natural numbers, adds them together, and gives me another natural number, or another number, the closure property of plus states that, let's talk about this analogy in our mathematics, or arithmetic rather. So if you have two numbers, A sub 1 belonging to the natural numbers, and B sub 1 belonging to the natural numbers, the closure of the plus operation states that A sub 1 plus B sub 1 belongs to the natural numbers, which is perfectly fine, right? It's basically, it's not even difficult to see, although as intuitive as it sounds, it may be a little difficult to prove. But if you pick two natural numbers, 1 and 2000, and gazillion and 2 gazillions for that matter, and you add them together, you still get a number that is still a natural number. We call this a closure property, or we say that plus is, or rather the set of natural numbers is closed under the plus operator. Okay. Now that I showed you an analogy in the arithmetic with the plus operator, and you saw that, oh yeah, adding two natural numbers will still get a natural number, so you saw something that is closed. Let me show you something that's not closed, right? That the set of natural numbers is not closed over this operation. And that should give you a flavor of the other side of the table as well. So the division operation is an operation that the set of natural numbers is not closed under it. So the set of natural numbers is not, I'm just messing up my board here. So the set of natural numbers is not closed under the division operation. Okay, and that's obvious. If you divide 1 over 2, you get 0.5, which obviously is not a natural number, right? So proving the division was easier. All it takes is a counterexample, and I just gave you the counterexample. So certain operations, set of natural numbers is closed under. For certain operations, it's not. The plus is an operation that a set of natural number is closed. So we say that closure property stands. Now, what I'm attempting to prove here to you is that the class of regular languages is closed under the union operation. That is, if I have two regular languages, A sub 1 and A sub 2, then their union is also a regular language. What does this actually mean? And why is it an important theorem for us? It means that if you have two languages that are regular, then what you know by definition 1.6 or something that we talked about earlier in the unit, if I have a regular language, then some automata recognizes it, right? Which means that I can make an automata for a regular language. Now, if I have two regular languages, then I can find two finite automata that can recognize these. One automata for the first one, the second automata for the second one. And according to this theorem, their union is going to be a regular language, which means that I can make an automata for their union as well. Now, why is it important? Just by just looking at the union here, if I have a set A and a set B, and each of them they've got two elements in them, their union is a bigger language, right? So the importance of this theorem actually is here, that if, according to this theorem, if it is true, which it is, if the regular if the regular languages are closed under the union operation, and if I have a language that is complicated, but I can break it down into the union of two simpler languages, then I can go ahead and build automata for those simpler languages, and therefore create an automata for my bigger language. And this closure property effectively guarantees that I can do something like this. So all that talk, let's now go ahead and see how we can prove this theorem. It should be quite abstract to you at this point, but what I'm going to do is that we're going to take a couple of steps, actually a number of steps, and step by step slowly build towards the proof. And as a byproduct of doing so, we will actually construct a toolbox that would also not only would prove that the set of regular languages is closed under union, it also gives us a recipe to create the regular language, or rather the automata from the simpler automaton for the union for the union language. So the idea here is this, that we have two languages, A sub 1 and A sub 2, and we know that both of these are regular. Since these two are regular, we know by definition that some finite automaton M sub 1 will recognize A sub 1, and some other finite automaton M sub 2 will recognize M sub 2, A sub 2, right? Now again, going back to our definitions, and we write these beautiful math stuff instead of the beautiful English language to just carry those meanings. So when I say that whole big sentence, that there is an automaton M sub 1 such that it recognizes the language A sub 1, the way that I would write it mathematically is this: L, or language of M sub 1, is equal to A sub 1. Meaning that M sub 1 recognizes A sub 1. And since A sub 2 was regular, then there is an automaton that recognizes it. And M sub 2 is that automaton. Mathematically, we say L of M sub 2 is equal to A sub 2. The language of M sub 2 is A sub 2. Okay? So that this is now beautiful. We have now two automaton, M sub 1 and M sub 2, that each of these automaton would recognize our languages, one of the languages. And now what we're going to do is that we are going to combine these two automata with each other to make the bigger automata, the overall automata, recognize the union of these two languages. And this is basically proof by construction. What we will do is that we'll just go through what we did with designing an automaton. We go through the so-called reader as automaton strategy. We put ourselves instead of the bigger automaton, knowing that we have at our disposal each of these smaller automaton, m sub 1 and m sub 2. Then what we're going to do is that we're going to see what would we do if we were that big automaton to recognize these languages. Now here's the point. See, if I have a string that is a member of a sub 1, then by nature that string would be a member of the union, right? If I have a string that's a member of a sub 2, then by nature of the union operation, that string would be in the union as well, right? Which is what I'm going to utilize. Now, if I were the bigger automaton, here's what I would do. I would go ahead and I would have this automaton number 1 and this automaton number 2, and then I would have a string that comes to me, and I need to recognize it. Then the idea is to simulate these two automaton m sub 1 and m sub 2 simultaneously for every string, and then at the end of my long string of inputs, if either one of these two automata accepted the language, then I will accept that language too, or that string too. So the idea is like this. Think of you having these two automaton, m sub 1 and m sub 2. Okay? And so m sub 1 has some start state, and m sub 2 has some other start state. And oops, actually start state was the one with the little arrow pointing to it. And then they've got a bunch of intermediate states, and then each of them will have their own set of accept states as well. Okay? So if a string comes in, right? So this is a string that I need to recognize. Let's say that this string is 0, 1, 0, 1, 1, 1, 0, blah, blah. So if I only had automaton m sub 1, then I would pass each of these elements to this automaton, right? And I would go through all those transitions one at a time. And then when I was done with this, with the last element, if I was in an accept state, I would recognize that string. I would accept that string. And if I ended up in a non-accept state, then I would just reject that string. That's what automaton number 1 does. The automaton number 2 does the same thing. It goes through and reads every single one of those steps, those symbols, and goes through the transition functions and labors through them. And when it reaches the last element, the last symbol, then it looks to see if it is in an accept state or if it is not in an accept state. If it were in an accept state, it would recognize that string. If it were not in an accept state, then it would reject that string. So now my job as the bigger automaton is basically to do this, to simulate these two smaller automaton, m sub 1 and m sub 2. So I take one element and then I pass it simultaneously to both of these automaton. Then I go to the next element and I pass that element simultaneously to both of these automaton. And the third element, pass it to both of these automaton. So basically in parallel, I would simulate my strings, and then when I'm done with the last symbol in the string, then I would look to see if I'm in either one of the accept states of the two automaton. If I were in the accept state of either one of the two automaton, or in a state that's the accept state of both automaton, then I would accept. If not, then I would reject that string. That's what I'm going to do. The reason that I need to be careful, though, is that you see, once each symbol is processed, it's gone. There's no such thing as going back and rewinding the tape, right? So that's why we cannot really put these two automatons right after another. Because when this automaton is processed, this first string, then or the first symbol in the element, then it's gone. That's the reason that we're simultaneously simulating the two automaton for every single element at the same time. Now, here's one big question that I have for you, and I'll give you probably a couple of seconds to think about it until I catch my breath. But the question I have for you is, how would you go about simulate the two automaton together at the same time. I feel like playing that little Jeopardy song too. Okay, so here is my answer. I have an automaton M sub 1, and M sub 1 has a set of state, and I call them Q sub 1. Actually, let's call them Q sub 1 1. No, let's call them Q sub 1. So M sub 1 has a set of states Q sub 1, and of course it has a sigma and blah blah. At this point I'm not really interested in those yet. And M sub 2 is another automaton, the second automaton, and it has a set of states Q sub 2. Okay? So let's actually draw these Q sub 1 and Q sub 2's here. Spell them out. And I call them Q sub 1 1, Q sub 1 2, Q sub 1 3, and Q sub 1 K. My handwriting is awful. And then Q sub 2, the set of my second automaton states, is Q sub 2 1, Q sub 2 2, all the way to, say, Q sub 2 H. Okay. So these are the sets of my automatons. So let's say that if I'm in some Q sub 1 something in automaton number 1, and a symbol comes in, I look at the transition function of that automaton, and I see in which of these other states I would go to, right? So that's what I do. So I basically start from one of these. Let's say that for simplicity, let's say that Q11 is the start state, and then same thing here. Let's say that this Q sub 21 is start state, because you know what, naming of my states are my own business, really. They don't matter. So I just order my states in such a way that the Q sub 11 and Q sub 21 are the start states of the first and the second automaton. So when I start my work here, so I go through, like, the first symbol I go here, then at the second symbol I go here, then the third symbol I go here, then the fourth symbol I go here, and so on and so forth. That's how my automaton number 1 works. Same thing here. So let's say that automaton number 2 starts from Q2 sub 1, and then goes here over the first element symbol, the second symbol, the third symbol, and then the fourth symbol, and stuff like that. That's how that automaton works. So how can I combine these automaton to simulate them simultaneously? There's an elegant way of doing this, and that is make a set of states that's the cross product of Q sub 1 and Q sub 2. If you create a set of states of these cross products, then effectively for each element of this new set that you created, you've got 2 states. One from the first state, Q11, and one from the second state, Q21. And then for each of the Q11s from the first state, the first automaton, you get to use one of the second automatons too. So Q2 sub 2. And then Q11 and Q2 sub 3. All the way to Q11 and Q2 sub H, the last state there. And then for Q2 of the first element, the first automaton, you have a combinations of all of the states in, actually 1 2, in the second automata, and all the way to Q1 2, comma Q2H. And it goes all the way to your last state of your first automaton, combined with every state of your second automaton. So then it's going to be 1K, comma to Q22, and all the way to Q1K, comma Q2H. And this will be the big set of states for us. Now, what's really great about this? See, I want to simulate the two automatons simultaneously, which means that at some point in time, my first automaton may be in some state, my second automaton may be in some other state. And then the next symbol, the first automaton will go to one of its own states, any number of them, and the second automaton may move to any number of its own states, right? So in this case, when I put them together in these ordered pairs like this with cross product of the two sets, then you see this will be my start state. Because when I start, my automaton number 1 is going to be in Q sub 1, 1. My automaton number 2 is going to be in Q sub 2, 2, 2, 1, right? The two start states. So I'm going to be in here. Now the next time, when my first automaton moves on the same symbol to, let's say, Q1, 2, it's going to be in one of these guys. And then my automaton number 2 goes to from Q21 to Q2H, then it's going to go here. So then, see, immediately I will immediately have access, by this byproduct, I will have access to this pair of states simultaneously at the same time. See, then I can just jump over here, right? Because like if this was my first move here and this was my first move for this machine, then the combination of the two machines, when I simulate them side by side, then it goes into this state over here. Now let's say that for this guy it goes to, from Q21 goes to Q1K, and then let's say that from Q2H I go to Q22, right? Then I'm going to go Q1K and Q22, which is this pair, right? So then I jump through to this state, right? So now I have a mechanism to simultaneously process one symbol, process two automatons side by side. Then for the next symbol, process two automatons side by side and see where I go in terms of the combinations of the new states that arrive. Okay, so this is how I will simultaneously work with both of my automata. So this is really shaping up to be a really great construction for me. So here's what I'm going to construct then that proves my theorem. I'm going to say, by the way, if I have k states in the original automaton, in the first automaton, and h states in the second automaton, so if the length of this guy is k states, and the length of this guy is h states, then my big automaton will have k times h elements in it. Or here, let's call them pairs. So the automaton that recognizes the combination is going to be k times h number of states. So for example, if this guy has 3 states and this guy has 5 states, then this will have 15 states in it. Now some of those states will be useless and you can trim them out, like a state that doesn't have any incoming transition into it, that will obviously never be reached, so you can just delete it. There may be some state that they may be effectively repetitions of each other, so you can combine those things to with each other, and you will end up with less states probably, but the maximum number of states that your resulting automaton for union of two languages will have is going to be k times h number of states, k being the number of the first element, the first automaton, the number of sets in the first automaton, and h being the number of sets in the second automaton. So so that is basically the maximum number of states that you should expect that your final combined automaton will have. So we'll say that here then, you know what, actually let me just go to my board, because that gives me a little bit probably more space to work with. So here we go, and I've got to delete a bunch of these things. Okay, this should be plenty for me to start working. Okay, so let actually at this point, whoops. So let m sub 1 to be the first automaton that recognizes A sub 1. Or in other words, let L of M sub 1 be A sub 1. Then M sub 1 is actually something like this. Q sub 1 from sigma, my input alphabet. For simplicity, we'll consider the sigma for both automaton to be the same thing. Makes my life easier, but if the two sigmas are different, for the final automaton, we just union the two sigmas. And then we call this delta sub 1, and then let Q sub 1 1 to be the start state of this guy, and let the F1 be the accept state of the first automaton. Okay, so this is how my first automaton would look like. Now, let also, so this I know, let also L, language of M sub 2, be A sub 2. Okay, then M sub 2 will be a 5-tuple as well. It will have a 5-tuple automaton that recognizes that language. Here I call this Q sub 2, sigma, and the transition function for this guy I'm going to call delta sub 2. The start state for the second one, I'm going to call it Q2 1. And then for its accept state, I'm going to call its set of accept states F sub 2. Now, just to simplify my life a little bit more, here on the side of the board, I'm going to basically say that for Q sub 1 and I belongs to Q sub 1, and then Q2 sub 2j belongs to Q sub 2. See, when you see a Q with two numbers at the bottom of it, the first number is which automaton it comes from, and the second number is which state in that automaton it is. Okay, so as a result, you see here Q11 is the start state of the first automaton, and Q21 is the start state of the second automaton. So basically, the first number is which automaton it was from, which machine, and then the second is which state, if you were really interested in individual states in that sense. So these are my two automaton that recognize my original languages. Then the way that I'm going to do this is I'm going to create M to be this automaton, Q sigma delta, and then Q sub 1 1 and Q sub 2 1 a pair, and F to be a finite automaton. So now to define this finite automaton, to show that this actually accepts the union of the two languages, I'm going to have to do exactly like what I did so far in this class. Define every single one of these guys. Q, sigma, delta, your start state and your final state. Now, let's actually start with the easy ones. So first, I'm going to just write down Q here. I need to see what this is. I need to see what this is. I need to see what this is, the delta. I need to see what my initial state is. And I need to see what my final states or accept states are. And if, as soon as I define all these 5, then I have proven my theorem. Okay? So let's start with the easiest one. The easiest one is actually the sigma. Since the two languages that I had the same sigma, as I said, I assumed, right? So sigma here and sigma here are the same. So the sigma for my combined language is the same. Now, if the language of the first one was sigma sub 1 and the second one was sigma sub 2, then the union of the languages would be, the alphabet for the union will be the union of the two sigmas, and my theorem wouldn't change at all. So so it's easy. So that's out of the way. Also, this was out of the way. Remember, when I have a sequence of, let's say, alpha, beta, gamma, and stuff like that that comes in, I want to start with the initial state of both of my my automaton. So Q sub 1 1 and Q sub 2 1. I want to start with both of the start states. So as a result of that, this will be the start state of M. Okay, so Q sub 0 will be a pair of the first start state for the first automaton and the second start state, or the start state of the second automaton combined together, so that when I see the first symbol in my string, I know where to start, right? So that is also done. So this is created. Number 4 is created. Now, number 1 is the next easy thing to create, and I just talked about it really informally earlier, is that since I'm taking each symbol one at a time and I want to side by side in parallel simulate both of my automaton, what I'm going to do is that I'm going to make the state of my big automaton to be a pair of a state from the first automaton and a state from the second automaton. This way I will have access to all of the states in both automaton at the same time at every time to be able to process. So as a result of this, I'm going to create my set of Q for the M to be the cross product of Q sub 1 and Q sub 2. So take the state of the first one, the set of states of Q sub 2, the second one, cross product the two, you get the set of states for your automaton that would recognize their union. How would that look like? It would look like something like this. Q1I and Q sub 2J, such that Q sub 1I belongs to Q sub 1 and Q sub 2J belongs to Q sub 2. So the first element of the pair comes from the first automaton, the second element of the pair comes from the second automaton. I create this cross product for every single one of those, actually these pairs for every single combinations of the two set of states, and that will give me the set of the state for the union. So now I can do my processing. The next fun thing is, so this is done. So I'm done with that. The next fun thing is to design my delta. Now, what I need to do is to look at my deltas for each of the automaton that I had. So let's go ahead and now let's design our, let me call it transition function. Delta. Okay. So one of the things that I know that this delta is, actually I need to define, is its domain and range. So the domain of this is from Q, the set, cross alphabet, over to Q. So this is effectively by definition. So my delta will take something from Q multiplied by, or rather cross product of alphabet, and then as a result it will produce something from Q. Now remember what Q was? Q was basically a pair of states, right? A pair of states. The first element from the first set, first automaton, the second element from the second automaton. Sigma was my alphabet, and Q is basically paired states, right? So in delta, the way that it would look like, it would look something like this. Delta of a pair and a symbol, let's call this A, that would result into a pair, right? So delta as an input takes a pair of states and a symbol from alphabet. and then what it would produce is a pair of states. So far I haven't done any magic. This is basically a result of me creating my Q for M to be the cross product of these two guys. So that's what makes the first element of my delta to be a pair of states. And then the second element comes from my symbol. That's fine. And let me just draw this out for you in terms of the more familiar table format that we've seen so far, right? So the way that it looks like is that delta is basically from Q cross sigma. So sigma here, remember, it was alphabet A, B, C, D, whatnot. And these guys were Q sub somethings, right? So in my case, I've got Q11, Q21, and then I've got Q12, Q21, and then a pair Q12, 3 actually, Q21, all the way down to Q1K, let's say, and Q2H, right? So if K and H were maximum Qs that I had. So this is basically all of the pairs of states that are out there. But remember, the only caveat is that the pair of states such that the first state comes from the first automaton, and the second state in that pair comes from the second automaton. Remember, the first pair comes from this guy, and the second one comes from this guy, right? That's why I put this 1 1 1 2 1 3 and 2 1 2 2 2 3 and so forth down here, just to avoid that kind of confusion, right? So the first state always has its subscript to be effectively 1, and then the second in the pair will always have its subscript to start with a 2. Okay? And then as a result of going to each of these guys, then it's going to produce a pair of states here, right? So each of these symbols will produce a pair of states, and that's how my function would look like. Now, how would it look like in terms of their diagrams? So if I had my M sub 1 to be something, oh, I don't know, like this, that had a start state, right? And then a bunch of state like that, and then an end state here. So let's call these like this, like A, B, C, and D. And then the other automaton, just to make it a little simpler, let's say that this is 1 and this is 2, and then the accept state is 3, right? And so for now, let's consider something like this. Just for simplicity, okay? So we go from A to B to let's make this C and D. It's easier to see. And then we go from 1 to 2 to 3 and back to 1. Okay, so then my pairs of states are going to be something like this. Actually, why did I create 14? 4 and 2, because this way I've got like 12 states to do. So my states are going to look something like this: A, comma 1, and then B, comma, or rather, let's start with A, comma 2, and then A, comma 3, and then B, comma 1, and then B, comma 2, and then B, comma 3, right? And then my elements, let's say my numbers were 0 and 1. So then here, I'm going to go like this. Like, what would I do if like 0 comes in? And I'm in A1, right? So I'm in A1. What would I do when 0 comes in? Then I see what M sub 1 does. So let's say that M sub 1 goes from A to B. So then this goes to B. And then I see simultaneously what M sub 2 does. Let's say that M sub 2 stays in 1 for that, for 0, for example, right? So then it goes to B, comma 1, right? And then let's say that for 1, then A goes to, I don't know, like C for 1, right? Then here I say A goes to C, and then B for 1 goes to 2. and so on and so forth. This is exactly how I simulate both m sub 1 and m sub 2. Okay, together. I mean, simultaneously, actually. If I can spell it. Okay, so this is how I simultaneously simulate this. Now, the core of my calculation is actually here. Now, I just now let's get serious. Now let's get really very, very serious, because now is when I would like to go ahead and start defining my computation here. Let's get serious. Okay, so this is informally I showed you in table what happens. This is informally I showed you in picture what happens. So in picture I showed you how to simultaneously simulate my two automatons side by side. In table I showed you how to simultaneously simulate my automaton. Now let me show you how in math simultaneously to simulate the two automaton. So what I need to do is to define the delta. Delta is at the core of my computation. What happens when I'm in a state in my automaton that's a combination of the two automata, and then I see a symbol? What would I do? This is what I would do. The delta of a state Q sub I don't know 1I comma Q sub 2J. Okay, remember 1 denotes that the first state belongs to the first automaton. 2 denotes that the second state belongs to the second automaton. So if you're in that state in your combined automata, and your combined automata is when you have all of these guys together, right? When you're in this state, and then you see an element, and let's call this element A, then here's where you end up. You end up processing your first automaton, and then the second automaton, and then plug them in. So you process the first automaton, and then the second automaton, and then plug them in. So I'm going to plug my first automaton here, the result of its computation, and then I'm going to plug the result of my second automata's computation here. Now, the good news is that here I've got my first automaton's computation and my second automaton computation there. I know that the delta 1 of, let's say, Q1J and A goes to some Q1K, right? It goes to some Q1K. And from the delta of there I know. And from the delta of here, I also know that the delta sub 2 of Q2J over that element, because I already have that, it goes to some Q2, I don't know, M, right? Then for the fun of it, let's just call this one also N. Q1N and Q2N. Okay? So then all I need to do is to plug in this element. This is the process of the first automaton. This guy is the process of my second automaton. Okay, so all I need to do is then to take this and break it down to use delta sub 1 of Q1I comma A, and delta sub 2 of Q2 J and A. Okay, so see, this Q goes in here. This Q, the second Q, goes in here. And what I will use is I use the delta 1 for the first one and the delta 2 for the second one, which is really, really easy, because now let's say that we've got something like this. We've got delta 1, let's say A and B, and so it's Q11 and Q12, and then we've got delta 2's A and B, and we've got Q21 and Q22. And let's say that this stays in Q11, this goes to Q12, this goes to Q12, and this goes to Q12, and let's say that this guy goes to Q22, Q22, Q21, and Q21. Okay, so let's just suppose that this was the case. I just demonstrated for you. Then I know that my combined delta would be something like this. Would be pairs of Q11 and Q21, and then Q11 and Q22, and then Q12 and Q21, and then would be a pair of Q22 and Q12. The first one comes from the first, the second one comes from the second, so Q22. Okay, so I know that this delta will be from pairs here over to the sigmas, which is still A and B. So then when I'm gonna process this, I'm gonna end up, for each of these symbols, I'm gonna end up in a pair of states. Where is the first element? What is this guy, right? How can I calculate this guy? To calculate this guy, you go in and then you see where Q sub 1 go for A in delta 1. So we see where Q sub 1 goes over A in delta 1. It stays in Q sub 1 1. So this is going to be Q sub 1 1. Then when we're done with the first one, we go to the second one. Where does Q sub 2 goes over A in delta 2? So Q sub 2 over A goes to Q sub 2 2. So it's going to go to Q sub 2 2 over A. And we'll do the same process for every one of these guys. So we go Q sub 1 1 from B in the first element, the first DFA. So Q11, if it sees B, it goes to Q12. So this guy is going to be Q12. And then this guy is going to be Q22. And so on and so forth. And this way you'll be able to calculate your unionized automaton like this, right? So here, this is what I did. I constructed my automaton to simulate the two smaller automatons side by side in this bigger computation, and this is how formally I define my my computation based on the computations of the original automaton M sub 1 and automaton M sub 2, right? Since I already have the delta sub 1 and delta sub 2, what I'm going to do is I'm going to use those two elements to calculate the computation of my combined my combined machine. So this is good. Now I proved my third section too, or rather I constructed something that takes care of the third element of my resulting automaton, and that is its transition function. Now finally, for the fifth element is, what is F? Okay. Now it's really now easy to see. When I'm done with processing my elements, my symbols, all I need to do is to see if any of, or rather, if the pair of states that I'm in belongs to either one of these two final states, which means that the accept state of my combined automaton is going to be a pair R sub 1 n and R sub 2 M such that R sub 1 M belongs to, rather, R sub 1 N, the first one is N, such that R sub 1 N belongs to F sub 1. So if the first member, if either one of the members is a member of an accept state, or if R sub 2 N belongs to F sub 2. If that were the case, then I accept. If not, then I reject that string. So you process your symbols of the string simultaneously. You end up with a pair of states every time, and when you're done with your string, you end up with a pair of states, and you look and see if that pair of states, if the first element is in the final state of the first automaton, or the second element is the final state of the, or rather the accept state of the second automaton. If either one of these two is met, you are good. So you ended up with any of these accept states, and that proves my my fifth element. So then I constructed an automaton based on my two original automata, M sub 1 and M sub 2. I build the Q, I build the alphabet, I build the transition function down here, right? This is my transition function. I build my initial state, which is the initial state of both of the elements, both of the automata. And also, I built the final state, which is going to be that guy. And now I'm good. I have an automata that accepts the union of the two languages, and therefore I proved that the union operation is closed, or rather the set of regular languages is closed under the union operation. So all that, long story short, is proof by construction. What I did is that I constructed M to be Q, sigma, delta, it's Q sub 0, and it's F. And I built all these 5 elements. Q is the cross product of Q sub 1 and Q sub 2. Sigma is the original sigma if both alphabet were the same, or if the two alphabet were not the same, then it's the union of the two alphabets. Delta is a function that's from the cross product of Q sub 1, Q sub 2, cross of alphabet over to Q sub 1 cross Q sub 2. And this is how my delta looks like. The delta of a pair Q1, comma Q2 over a symbol A is equal to a pair. The first element of the pair is delta sub 1 of Q1 and A. And the second element is the delta sub 2 of Q2, the second pair, and A. Okay, so basically this guy goes here, and this guy goes here. That's my delta. And for what is my Q sub 0? Q sub 0 is nothing but this start element of Q1 and the start state of Q2, where Q sub 10 is start state of M sub 1, and Q sub 20 is the start state of M sub 2. And finally, the set of accept states here is going to be a pair, any pair of states R sub 1 and R sub 2, such that R sub 1 belongs to the accept state of the first, or R sub 2 belongs to the accept state of the second. Okay, so if you end up with a pair of states after you're done with your computation, You look at either one of those two states. If each of them is in an accept state, then you accept the whole string. You reject the string if both of those states are not accept states. And this proves my theorem.